Buenas tardes, señoras y señores.
Good afternoon, ladies and gentlemen. I first want to thank Pedro Echenique, Alberto Galindo, and the Vice President of the Council who are with us here for their kindness in relation to this conference.
The first speaker this evening, Professor Sheldon Lee Glashow. Glashow was born in New York City in 1932 in Manhattan and always considers himself an East Coast man. He doesn't like California very much. He is of Jewish-Russian parents and who emigrated to the US around 1905. Spain, you see, is not the only country with anti-Semitic feelings. In the prestigious Bronx High School, he had classmates like Steve Weinberg and Gary Feinberg. University studies were carried out at Cornell University, again coinciding with Weinberg. And he did a PhD under the prestigious Professor Julian Swinga of Harvard. He has several postdoc positions at the Nielsborg Institute in Copenhagen, at Caltech in California, on the Maury-Gell-Mann, etc. His university career starts at Stanford when he was assistant professor, continuing at University of California in Berkeley, and then back to his beloved Harvard in 1964 as a full professor, and has been professor in Harvard until 1982, in which he became distinguished visiting scientist at Boston University, still in the Boston area. Now, Glashow was the first to understand the need for a neutral weak current to unify the weak electromagnetic forces, which was actually the theme of his thesis on the Swinga. He was the first also to propose the fourth quark and invented a name for it. The name has gone on. It's called the charm. Today we know it's a crucial ingredient in the validity of the Standard Model. With two collaborators, Iliopoulos and Mayani, they discovered what is called the G mechanism, which is a way to prevent the excess of neutral currents which conserve strangeness. As the confirmation of the Standard Model came up in the early 70s, he received the Nobel Prize for Physics in 1979, together with Steve Weinberg and Abdus Salam, who passed away not long ago. You see, there were two Jews and a Muslim. But to restore the balance, Professor Salam from Pakistan appeared in Stockholm with two wives, such to the embarrassment of the Stockholm authorities. Glashow has written 3 books that I know of, and one of them is in Spanish translation. It's called El Encanto de la Física. It's published by Tusquets in Barcelona, and I very much recommend that book to you. Glashow is skeptical of string theory, and he has a beautiful article in Physics Today some years ago, together with Paul Grispar, which is called Seeking Superstring Desperately, imitating the feel about Susan, you know, which I also recommend to you very much if you are also a bit skeptical about the strings. Glashow, as far as I know, has been in Spain several times and has collaborated especially with Álvaro de Rújula, a theoretical physicist who is now for a long time at CERN. And there's a famous paper of the two of them with other people, I believe it's also Politzer and perhaps Tom Appelquist, which is called Hadron Masses in the Gauge Theory, which was a crucial paper to make people accept the idea of the Standard Model, including gauge theories for both strong, weak and electromagnetic interactions. His wife, Joan, who is also here with us, although I don't know in this moment, and I know she loves very much the Basque seafood, perhaps she loves it too much. She's the sister of Lynn Margulis, a prestigious biologist who also has been, and it is connected with Spain. She's the inventor of the theory which is called the serial endosymbiotic theory, which is a biologic topic, so I will not bother you with that. To finish, let me just tell you a couple of phrases which I took from his books, and I will say them in the Spanish translation because I took from the Spanish translation of the book, and also because I don't want to embarrass him with the English of that. La física es un entretenimiento.
Physics is an entertainment, but it can also be an obsession. The only thing I regret about my parents is that they didn't live to see me collect the Nobel Prize. There are many Californians of Basque origin, immigrants directed to being shepherds, And the telegram to Blas Cabrera, is the grandson of his grandfather, and people will know what I mean, when he tried to discover the magnetic monopole on St. Valentine's Day, 14th of February 1982. And Glashow wrote, "Red is the road. It's time to see another monopole, because no other was ever seen." With you, Professor Sheldon Glashow.
Well, thank you so much for that overly generous introduction. It's really a great pleasure to be here. I'd like to say a few words of thank you to our hosts for bringing us to this gem of a city. And in just a few days, we've done so many different things, in addition to my wife getting a bit of the flu. We've watched a road race along the streets of the city. We've visited a spectacular beach filled with people on a sunny day. We participated in a cider festival. We climbed to the Castillo overlooking the city. We bathed, exercised, and played at La Perla. We had pinchos in half a dozen different places in the old town. We ate at several gourmet restaurants. We watched a bunch of students demonstrating, I don't know what they were demonstrating, but they were throwing tomatoes at the town hall. We saw the semifinals of the boat race. We watched a demonstration of Basque versification. We've walked throughout the city and enjoyed its splendid architecture, the Art Deco buildings, and I'm indeed awestruck at the size of this audience. This is a series of highly technical talks. This room appears to be full. There are hundreds of people. This could not possibly be done in Boston or Paris or Rome or Bangkok, but somehow here people are interested in science more than any town I've ever seen. I'm very impressed. And furthermore, lastly, I must admit to being a bit jealous after hearing the incredibly enlightened speech by the President of the Basque Republic. I only wish we had politicians in my country who had that level of wisdom. Now, my lecture will be in two parts. And unlike the other lectures, it's in radio, not television. I have no pretty pictures for you to watch, just words. I shall begin by deconstructing the phrase unified field theory. I shall then turn to Einstein, and after touching briefly on the marvelous accomplishments of the miracle year, which we're celebrating, I shall explain what led Einstein to his stubborn, persistent, and doomed search for a unified theory, and what leads many physicists today, many of the best and brightest theorists, to the renewal of this quest in the form of superstring theory, or, as the press would call it, the theory of everything. Thus we shall see how history can repeat itself even in science. My personal view of superstring theory may be summarized by an anonymous quotation I found in the Oxford English Dictionary. Quote, "Unification may be pleasant to the unifier, but never to the unified." Indeed, I'm the only speaker at this event whose subject does not exist. There simply isn't any such thing as Einstein imagined. There is no unified field theory. And as a result of that, my talk may be a bit shorter than those of my colleagues. What do we mean by a scientific theory? Here are two dictionary definitions. A theory may be a scheme or a system of ideas or statements held as an explanation or an account of a group of facts or phenomena. Or a theory may be a system of rules, principles, and procedures devised to analyze, predict, or explain the nature or behavior of a specified set of phenomena. Implicit in these definitions is the requirement that the system of rules comprising a theory must be self-consistent and coherent. Moreover, both definitions clearly indicate that a theory must have a well-defined envelope of validity. Within this domain, a theory must be subject to verification, to test by experiment or by observation. That is, to be a theory, a system of ideas must be both predictive and falsifiable. Let me give an example of a theory, Newton's laws of motion. Stated very succinctly, they are: 1, the persistence of uniform motion in the absence of external influences; 2, F equals ma, and the notion of force as the agent of acceleration; and 3, the last law, the law of action and reaction, which says that when an apple falls on your head, the force that you experience is equal and opposite to the force experienced by the apple. These three laws, along with Newton's gravitational law and certain rules of procedure, such as the means by which different forces are to be combined with one another, constitute what is known and taught as classical mechanics. It is a powerful and predictive theory. It let Newton understand motion on Earth and motion in the heavens, and it led his successors to the discovery of planet Neptune. More recently, classical mechanics helped us launch satellites into orbit, send men to the moon, and put robots on Mars. Maybe someday we will people on Mars, but I doubt it. The discipline remains as useful as ever. It continues to be taught, even though we have known for many decades that classical mechanics is wrong, it is fatally flawed. Consider, classical mechanics fails whenever things move so rapidly that Einstein's special theory of relativity becomes important. Classical mechanics also fails whenever things are so small that quantum mechanics becomes important. And classical mechanics also fails whenever things are so dense and so massive that Einstein's general theory of relativity becomes important. Nevertheless, Newton's mechanics is still taught at every school because it works where it is expected to work. It is, in fact, a correct theory, a self-consistent system of rules whose envelope of applicability has been precisely mapped. In the facile words of a colleague of mine, to be accepted as true, a theory must be shown to be false. Except, of course, for a hypothetical but never to exist theory of everything. What we say about classical mechanics applies just as well to many other old but useful disciplines, such as Maxwell's electrodynamics, thermodynamics, fluid dynamics, and Schrödinger's quantum mechanics. We know exactly under what circumstances and just how well each of these theories should work. The same cannot be said for all of our current theories. The precise envelopes of validity for quantum field theory, for general relativity, and for Big Bang cosmology are not yet determined. So much for theories. Let us now turn to the word unified, one of whose dictionary definitions is, quote, linked, consolidated, or associated, to be made into a coherent whole. One way in which a scientific discipline can be said to be unified lies in the sense of its being universal. Thus, the theory of evolution is unified because it pertains to every living organism, from the tiniest virus to the most majestic tree, and to our very selves. Indeed, all of the wonders of the living world appear to be consistent with the evolutionary doctrine of random variation and natural selection, which theory has passed every empirical test, despite the claim of the Church that, quote, an unguided evolutionary process simply cannot exist, and that such theories represent, quote, an abdication of human intelligence. Here I am quoting from a recent New York Times article by the Cardinal Archbishop of Vienna. Unfortunately, the unnecessary and destructive conflict between religion and science rages in my country as well, where Einstein's vague allusion to the old one has evolved into an intelligent designer as an alternative to rational science. The laws of physics may be said to be unified too, because they apply to phenomena on Earth and to phenomena in the heavens. They apply to everywhere and to every when, to everything, however large or small. Just as Newton may have understood lunar motion by considering a falling apple, so modern physicists have learned how stars shine from laboratory studies of nuclear reactions. In fact, the experimental study of neutrinos, which are among my favorite particles, the tiniest of all elementary particles, has led us to a detailed understanding of the titanic stellar explosions we call supernovae. Its unity and universality shows that science is in no sense a social construct, as some postmodern scholars have alleged. Imagine Arthur, an imaginary alien from an advanced society that thrived long, long ago on a galaxy far, far away, as my ex-brother-in-law Carl Sagan might have said. Arthur would surely have learnt about quarks, quasars, and quantum mechanics. It, he, she, or whatever, would have realized that its species, like ours, had evolved through natural selection over the ages from far simpler organisms. There are at least two other senses in which a theory can be said to be unified. Einstein created the special theory of relativity and helped lay the foundation of quantum mechanics. Yet these two disciplines did not seem to be compatible with one another. Schrödinger, to his distress, could not formulate a wave equation to describe the behavior of rapidly moving electrons. Just such a relativistic equation would be found later by Dirac in 1929, but its interpretation was obscure. It took some time for scientists to realize that the Dirac equation implied the existence of antimatter. Quote, "My equation was smarter than I was," Dirac once said to me on a Sicilian beach. 2 decades would pass before the marriage between quantum mechanics and special relativity was consummated. It was consummated by the work of Feynman, Schwinger, my advisor, and Tominaga, among others. Their theory, quantum electrodynamics, could certainly be said to have, quote, linked, consolidated, and associated two seemingly disparate disciplines. However, the entry for unified in the Oxford English Dictionary reveals the usage that is most relevant to this talk, to my talk. Unified field theory in physics, a field theory that describes two or more of the four interactions, originally gravitation and electromagnetism, previously described by separate theories. The earliest appearance of the phrase unified field theory that I can find is in an article written by Einstein in 1929. The purpose of my, quote, "The purpose of my work is to reduce to one formula the explanation of the field of gravity and the field of electromagnetism. For this reason, I, Einstein, call it a contribution to a unified field theory." Now, in point of fact, the first unified field theory precedes Einstein. It lies hidden within the word that we all know, electromagnetism. Long ago, electricity and magnetism appeared to be totally distinct phenomena. It's true that they had some properties in common. They both came in two varieties. Like charges repel one another, unlike charges repel. Like magnetic poles repel one another, unlike magnetic poles attract. But in other ways, electricity and magnetism seem to be quite different. Magnetic effects appear to be limited to iron-bearing materials, but electricity was promiscuous, totally promiscuous, because any body of any material, properly insulated, can be electrified. Furthermore, the electrical property can pass through wires from one body to another, but magnetism can be communicated from one body to another only by contact. The first real link between electricity and magnetism arose in the course of a lecture, arose in a lecture by Hans Christian Ørsted in 1810 in Copenhagen. Ørsted showed that an electric current produces magnetic effects. Half a century later, thanks to the work of Ampere and Faraday, and culminating in the work of Maxwell, a unified theory emerged that describes not only electricity and magnetism, but light and other forms of electromagnetic energy as well. It was the first unified field theory. And you will have noticed that in the course of my discussion, the word field has somehow slipped in, the last of the words that we must deconstruct. According to, again, to the Oxford English Dictionary, the meaning of field, as we use it in physics, is, quote, the area or space under the influence of or within the range of some agent, a state or situation in which a force is exerted on any objects of a particular kind, such as electrical charges, that are present. Faraday devised the concepts of electric and magnetic fields in 1845. They were alternatives to the then unsatisfying notion of action at a distance. Before Faraday, people believed that a magnet somehow exerts a force directly and instantaneously upon a nearby bit of iron. Faraday's field acts as an intermediary between these two objects. The magnet creates a field throughout all of space, and it is this magnetic field that acts on the bit of iron. Thus, a field, as used in physics, electric, magnetic, or gravitational, is a contingent construct, one that describes what the force would be at any point in space where a test object placed at that point. In his textbook, his treatise on electricity and magnetism of 1861, Maxwell wrote that Faraday saw lines of force traversing all space, that is, electric and magnetic fields, where the mathematicians saw centers of force acting at a distance. Faraday saw a medium where they saw nothing but distance. Faraday sought the seat of the phenomena in real actions going on in the medium, but they were satisfied that they had found it in the power of action at a distance. Although Faraday introduced for us the notions of fields, he and Maxwell as well were quite wrong about that medium that they refer to, also known as the ether or the luminiferous ether. Einstein, as you know, would do away with that fancy, just as Lavoisier had abolished phlogiston, the presumed agent of fire, and Count Rumford, who was once a spy for the British against the Americans, expunged caloric, the presumed agent of heat. Maxwell's theory is a field theory. His equations allow one to determine the electric and magnetic fields that are produced by moving charged bodies, whose motion is in turn determined by these fields. So also is Newton's theory of gravity, a field theory. The motions of heavenly bodies are caused by gravitational fields which they themselves generate. But in the quantum world, fields have developed a far more general meaning, one which Einstein reluctantly led us toward, but one that he never accepted. Today's quantum field if I may digress, is an operator that describes the creation and destruction of elementary particles. But that's another subject, the subject for another lecture. And so, having fully completed our deconstruction of the phrase unified field theory, let us go on to discuss its most fervent and famous champion, the great man himself, Albert Einstein. We have gathered here to celebrate the centennial of Einstein's Annus Mirabilis. But please remember, his 5 remarkable works of 1905 had nothing at all to do with unified field theories. The first paper of that great year extended Planck's notion of the quantum nature of light. Einstein wrote that the energy of light is not distributed continuously, but consists of a finite number of energy quanta that move without dividing and can be absorbed or generated only as complete units. Monochromatic radiation of a single frequency, behaves as if it consists of mutually independent quanta of magnitude of energy, hf, where h is Planck's constant and f is the frequency. Today we call the particle avatars of light photons. Einstein's explanation of the photoelectric effect in terms of photons, for which he would eventually receive the Nobel Prize 17 years later, was an immediate consequence of these ideas. More importantly, his work led Niels Bohr and his successors, such as Schrödinger and Heisenberg and Max Born, to the development of quantum mechanics, one of the 2 great pillars of modern science. Einstein's next 2 works of that year were his thesis, A New Determination of Molecular Dimensions, and his paper on the then mystifying Brownian motion, about which you have already heard. These works offered decisive evidence for the validity of kinetic theory, and hence they affirmed the existence, the actuality of atoms and molecules. Einstein then created the second pillar of modern physics in June of 1905. His exposition of the special theory of relativity reads almost as if it were written for a modern textbook. Oddly, it does not include the world's most famous equation, E equals mc squared. This result, in the form m equals E over c squared, awaited Einstein's second relativity paper, written in September of his miracle year, almost exactly a century ago. And it is because of that paper that we know today that when you charge your cell phone, it gets a little bit heavier, but only a tiny bit. The energy weighs. With his special theory of relativity, Einstein succeeded in reconciling Maxwell's theory of electromagnetism with Galileo's principle of relativity, the requirement that the laws of physics are the same to all uniformly moving observers, or equivalently, that there is no way to detect one's absolute motion in space. However, Einstein found that his theory was inadequate in 2 ways. It could not encompass gravitational phenomena, and its validity was limited to inertial coordinate systems, that is, uniformly moving coordinate systems. Einstein sensed that these 2 flaws were related to one another, but it took him over a decade to work out their connection. The result, as we all know, was his general theory of relativity, GR. GR had one immediate empirical success, which is worth an amusing digression. Soon after its discovery in 1791, the discovery of Uranus, the 7th planet, in 1791, scientists observed that its orbit was not quite in accord with the expectations of Newtonian theory. Either Newton's theory was wrong, or there had to be an undiscovered body perturbing the motion of Uranus. Following the latter hypothesis, John Couch-Adams in England and Urbain Le Verrier in France computed the orbit of what would turn out to be the 8th planet, Neptune, which was duly discovered in the year 1846. Shortly afterward, a small discrepancy was discovered in Neptune's orbit. In 1859, Leverrier, inspired by his earlier triumph, attributed the anomaly in Mercury's orbit to the existence of a new planet interior to Mercury's orbit. He named this hypothetical planet Vulcan, but he died before it was found. Vulcan wasn't found because Vulcan isn't there. In this case, Newton's theory was wrong. Mercury's anomalous motion was explained, finally, by Einstein's theory of general relativity. Now, resolving an anomaly is a good thing to do, but it's not quite the same as predicting something new. GR also predicted the bending of starlight passing by the sun, passing near the sun. At the time, this phenomenon could only be observed during a total solar eclipse. As the First World War intervened, Einstein wrote, "Only the intrigues of miserable people prevent the execution of the last new important test of my theory." Einstein's prediction was finally confirmed in 1919 at the end of the war. Revolution in science screamed the headlines of the London Times. New theory of the universe, Newtonian ideas overthrown. Overnight, Albert Einstein had become the world-famous celebrity he remains to this day. Not long afterward, in 1921, Einstein espoused his hope that, quote, "A generalization of the gravitational equations, his gravitational equations, will be found which includes the laws of the electromagnetic field." But he wondered whether, quote, "the formal connections so derived can really be regarded as an enrichment of physics, so long as it does not yield any new physical connections." Throughout his life, Einstein was aware of the danger of unfettered speculation that is not subject to experimental vindication. 2.5 centuries earlier, one of my heroes issued a very similar warning. Robert Hooke said, quote, "The science of nature has been too long made only a work of the brain and the fancy. It is now high time that it should return to the plainness and soundness of observations on material things." Just as Einstein, toward the end of his life, once again insisted that, quote, "experiment alone can decide upon truth." Nevertheless, Einstein would spend the last decades of his life in a ceaseless search for his ignus fatuus, or will of the wisp, a unified field theory of gravity and electromagnetism, one that would somehow explain the atomic structure of matter. To most physicists at that time as well, Einstein's failure was no surprise. Not only was Einstein reluctant to accept quantum theory, but he ignored the astonishing new discoveries. He seemed to be consciously unwilling to listen to the discoveries then being made about the subnuclear world. Einstein, in his later years, simply didn't know enough physics. A similar fate awaited 3 of the founding fathers of quantum mechanics, Erwin Schrödinger, and in a somewhat different context, Werner Heisenberg and Wolfgang Pauli. None of them had the least success in their quixotic attempts at unification. During the decades Einstein was fiddling with unified field theories, very much was happening along the road he had not taken. In the 1930s, we learned that atomic nuclei are made of protons and neutrons. Forces other than gravity and electromagnetism were needed. A strong force was needed to hold protons and neutrons together in the nucleus, and a weak nuclear force was necessary to let protons and neutrons to turn into one another. Yukawa's conjectured meson, and he actually called it the mesotron, which he vainly hoped could unify the 2 nuclear forces, was found in the 1940s. Powerful accelerators were built to explore the exciting new subnuclear frontier. Many seemingly elementary particles were discovered, but Einstein didn't care. Today we have a triumphant theory to describe three of the forces of nature, the modestly named Standard Model. In a sense, it is a unified theory, because all these forces are described by a quantum field theory of a certain sort, what we call a gauge theory. Our Standard Model offers what appears to be a correct, consistent, and virtually complete description of all as yet unobserved elementary particle phenomena. However, many questions in the subnuclear world remain unanswered, such as, why are there 6 kinds of quark, and how do they acquire their rather bizarre masses? How do neutrinos obtain their masses? Neutrinos were shown to have mass just a few years ago. Some of these questions are likely to be answered by the Large Hadron Collider, now under construction, now being completed at CERN. More disturbingly, though, the Standard Model does not describe gravity. More disturbing to some. Gravity is assuredly there, even though it is far too weak to have any relevance at all to elementary particle physics. So there is a perceived need for a quantum theory of gravity, even though it is also the general perception that a quantum theory of gravity would have no observable consequence. The search for a unique theory to encompass all of the particles and all of the forces of nature, gravity included, continues today. It is known as superstring theory, or string theory, and it has attracted the attention and commitment of many of my best and brightest colleagues. Last year, the 20th anniversary of the first string revolution was celebrated. And yet string theory appears to be just the sort of speculation that Einstein and Robert Hooke warned us about. It has neither predicted any new phenomena nor recapitulated the successes of the past. It seems in the past that a new theory to be accepted has to include the things, a description of the things we already know, and that is not true of string theory. Almost 2 decades ago, Paul Ginsberg and I wrote, quote, that string theory, unless it yields testable physical information, might be the sort of thing that Pauli would describe as not even wrong. The situation today, 18 years later, is much the same. Just last month, listen to this, a leading string theorist bragged to the New York Times that, quote, we have done very well without any experimental input, unquote, proudly. According to Lee Smolin, who is an advocate of an alternative to string theory, quote, a scientific theory that makes no predictions by which it could be contradicted by a doable experiment and which also has no precise mathematical formulation can never fail, nor can it succeed, quote, so long as science stands for the body of knowledge about which disagreements can be resolved by rational arguments from the evidence, and not by arguments from intelligent design, even if the designer is witty. I shall conclude with a few words on a slightly different subject, if I may, about rather early indeed. But nonetheless, I warned you that there is no such thing as a unified field theory, so I cannot discuss it for a full hour. There is a so-called conflict between, quote, emergence, which has to do with the appearance of complex collective phenomena, and, quote, reductionism, which deals with the basic stuff of matter and the rules by which these things combine with one another. Robert Laughlin, a Nobel laureate who shares my distaste for string theory, believes that physicists face a philosophical crisis today, that we live, quote, not at the end of discovery, but at the end of reductionism. a time in which the false ideology of human mastery of all things through microscopics is being swept away by events and reason. It is true, indeed, that our knowledge of neutrinos and neutron stars is quite irrelevant to such phenomena as superconductivity, life, or consciousness. Indeed, quarks and gluons play hardly any useful role in nuclear physics, and nuclear physics is pretty much irrelevant to the pursuits of chemistry and of biology. Similarly, what we have learnt about the origin of the universe and the evolution of stars and galaxies is entirely useless to anything practical down here on Earth. I see no philosophical conflict here. Rather, I feel that it is our duty, perhaps our sacred duty, to strive to understand as best we can the world we are born to, from the tiniest particle to the universe itself, to, if I may paraphrase the Bible, to all features, large and small, however emergent or reductionist they may be. The Italian Holocaust survivor and novelist Primo Levi said it best, and let me end with a quotation from him. What is the use of all this research? A world in which only useful things are studied would be sadder, poorer, and perhaps even more violent than the one that fate has allotted us. I believe, he wrote, that what is being discovered about the infinitely large and the infinitely small is sufficient to absolve this end of the century and the millennium. And I am sure that Einstein would agree. Thank you.